Hey everyone, welcome to the last talk of the conference. I know it's sad, but exciting. It's been a good conference. Our final speaker, our closing keynote, really needs no introduction. He's been around this community for a very long time. Some of his best books that you've probably heard of: Modern C++ Design, C++ Coding Standards. He worked on the D language for quite a while. He's currently the vice president of the D Language Foundation, but he also does some C++ from time to time. Please welcome Andrei Alexandrescu.
Thank you. Thanks very much. Before we even start, this color adds 10 pounds. Camera adds 10 pounds. That's another 10 pounds. So in reality, I'm very slim. You should know this. So thank you, Daisy. Daisy and I have had a nice exchange of emails a few weeks back. And it went like this. Daisy has this great series, Cute C++. It's just amazing what's going on there, right? And essentially, I sent her like a cold email asking, is it okay if I make fun of all of your cute C++ things? I pass them to ChatGPT, see what it does, and they might make fun of you, essentially. And I was like, of course, in nicer terms. But then Daisy's response was, great idea, how can I help? I really like that. But then I came with a different tack, which we're going to discuss today. So, fair warning. I know it's the end of the conference. Did you like it? All right. Do you know the phrase premature celebration? We still have 105 minutes. So curb your enthusiasm. So I know it's the last talk of the conference, and we're kind of tired. And the keynote is supposed to be fluffy. They asked me to be fluffy. And I say, I can't do fluff. I know math and code, and that's pretty much it. I can slap the keynote thing on it, and it's a tech talk, but it's actually not a keynote. So we're gonna have math, we're gonna have code, we're gonna have flashing lights. I know everybody's tired, so I'm going to insist more on intuition and high-level understanding rather than code minutia as it goes. So I have a reluctant fascination and a careless obsession, if you wish, of improving on algorithms that are not improvable. Which is kind of a weird place to. I didn't want to be that guy, but it's just a weird thing. Back in 2014, I wrote a few string-to-numeric and back algorithms that are now part of Meta's Folly library. Then 2017 comes, I wrote a paper for an algorithms conference called Fast Deterministic Selection, and it completely blows nth element out of the water. By the way, so I was very happy to see Pete Eason's talk yesterday about median, and it used nth element. And so it's a very useful algorithm. But nobody cared. I mean, nobody in the C++ community said, oh, let's implement that algorithm for the standard library. But I didn't cede. I kept on going. 2019 comes. I wrote a faster std make heap and std sort. Nobody cared. I discussed that in my CppCon 2019 talk, those nice days before the pandemic. And then 2000, that's wrong. It's not 2019. Oh yeah, that's right. Yeah, sorry. 2019 September, GPT-2 came out. And we laughed and laughed. I mean, did anyone try it? It was really funky. And for coders, it was hopeless. There's absolutely no chance. So it was kind of funny, and it was like it's like a monkey brain, chimpanzee who didn't do anything. It did utter some things, but very far from. But then, 2022, November 30, my birthday, they released ChatGPT with GPT 3.5 in tow. And we kept on laughing, but it wasn't the same laugh. It didn't sound the same. It sounded a bit forced. So then, I kept on going, and I said, oh, okay, so this is nice, Brave New World. And today we're going to talk about the faster STD binary search, the binary search algorithm. It has an interesting history going back literal centuries. Socrates, Aristotle, Plato, Euclid, those guys. I mean, as an aside, I wonder people living in those negative years, how do they know? Like, yeah, I was born in 438, minus 438. And hi, how are you? That's odd. It's kind of interesting how life was back then. So it was called method of dichotomies, and you can actually find it even in religious texts, Buddhist texts, and you can find it in all philosophy and everything. And essentially, it has to do with dividing sets in smaller sets and keeping, eliminating half of the set, and so on. There's stories in a variety of religious texts, like, I don't know, divide these people into crowds, and I don't know, kill half of the guys. I don't know what they did, and then keep the other half, and then continue. I don't know, something like that. And okay, since someone is having a lot of fun. All right. So then it evolved into the mathematical method of bisection. And bisection is, you cut an arc of a function and you figure out an approximation to the value of the function at the middle of the arc. So that's also interesting. And Descartes invented that. Bolzano was the first to formalize it. And then there's actually a new development in 1976, which is quite interesting because almost 200 years have passed before it was formalized properly. And binary search was first formulated as a computer science problem in 1946. And it took 11 years, up to 1957, for people to figure out what to do when n is not a power of 2. I know what you're thinking. You're thinking, I will travel back in time to 1947, and I'm going to show those people how it's done. Right? I don't know, I have these fantasies. So the power of binary search stands in, I'm sure everybody knows about it at a level. It stands in eliminating, actually it's not searching for a thing, but it's actually eliminating as possibilities as many elements for each comparison as possible. So your goal is less an obsession with the search value and more of a focus on eliminating candidates from the search. We're going to save a few comparisons in binary search. Not few, but it's not going to be 10x. It's not going to be like, oh yeah, I came in the year 2023 and 10x binary search with the same hardware. No, it's not going to be like that. It's going to be, you're going to save a few comparisons, right? Do I care? My friends, let's be honest. We are the Scrooges of computer science and engineering. We care about one comparison that is always predicted to be false. STD vector, bounds unchecked by default. And the bounds check in the vector indexing operator is absolutely the most predictable test there is in the world. So the branch predictor is going to have 100% success rate guaranteed, because otherwise it's going to throw, the application is probably going to end, and nothing good is going to come out of it. STD smart pointer, all smart pointers. We're not going to check that because we care about that test that can't be even measured. And to add insult to injury, STD optional operator arrow is unchecked. Don't you hate your life? I mean, okay, so here, work with me on this. Work with me. So let's define something that is optional. It means it could be there, it may not be there. Right? So far, so good. Are you with me? We're together in this? All right. Great. So that type is going to be encoding nicely the presence of something, because otherwise people are going to do silly things with unions and booleans and initialized data and all the nonsense, right? Good. So have a nice, safe type in the standard library. Oh, and I have an idea. Let's abuse this dereference operator to mean give me the value that's in there, if any. But then it's like, you know what? We designed all this great type. We spent 1,000 lines of code on it, and let's not check it. It could be there, but this operator is going to assume it's there. So, okay, if I'm going to say like one comparison in binary search, I'm going to be vindicated, my friends, okay? Let's be clear. Let's be clear about this. I'm going to be vindicated, okay? The list goes on and on. So today we're going to work on something that is better. No risk performance improvement for STD binary search and its friends. So you do care. Even if you don't know it, you do care. In your heart of hearts, you're thinking, I'm so happy that pointer, the smart pointer operator is not checked. Makes me feel so good. So let's look at binary search. As commonly taught, it is an absolute beauty of a loop, and it goes. I'm going to template it on the iterator type and the search type, and I'm going to loop as long as I have elements in the range, and then I'm going to cut in half the range. M gets B plus E minus B by 2. That would be half of the available range, and then I'm going to do 2 comparisons inside that loop. Careful. So the first one I'm going to say is the value that is strictly less than the middle element. In that case, I'm going to say, oh, then the new end is the middle because I don't care about anything to my right. Right? I'm looking for something that's on the left. Don't forget the range is sorted. Right? Otherwise, if it's not smaller, it's greater than or equal. So let's see, is it strictly greater than the search value? In that case, I'm going to say, oh, in that case, I don't care for anything on this side. So I'm going to say the new begin is that median plus 1. Plus 1 because, it can't, because essentially it's not smaller and it's not greater, so essentially it can't be any of the margins. And finally, in the last case, I'm going to say, oh, it's not smaller, it's not greater. Yay, I found it. Right? Notice how the focus is not on finding as much as on eliminating possibilities, right? So I gotta say, this algorithm produces, even today, it gives me an emotional reaction. So you go CS 101, remember the first loop you ever saw. The first linear search, 4 equals, what? 4, yeah, okay, so I'm doing a linear search. So you see the mechanics, you see the loop, you see the thing happening, and you're like, all right, what else is new? Right? So linear search is as you would do it in real life. You look like an idiot at every element until you find the one. Right? I mean, this is it. Not interesting. But then I say, oh, wait a second, if the range is sorted, there's this. When I saw this, I was like, who needs dating? This is my life. That was it. This algorithm has violet eyes. It is so beautiful that in this moment as I'm sharing it with you, it gives me an emotional reaction. I'm not going to cry, so, keeping it cool, right? But it's a great algorithm. I like it a lot. However, if you crack open your STD implementation, you're going to be a bit disappointed because you're going to say, oh, wait a second, binary search as implemented in STD, it does not look like the violet eyes algorithm. No, what it does is going to, let me call this lower bound function, which is distinct, and then I'm going to do one more test and return. So what's the deal with lower bound? Lower bound actually has a different task, but it's actually not as pretty, but it's a very effective algorithm, right? It's the algorithm you take with you on a hike in the mountains, right? It can carry a backpack, right? It's solid, it's strong. What it does is going to find the boundary between less than and greater or equal than. So everything to the left of the return iterator is going to be strictly less than what you're searching for, and everything else is going to be greater than or equal. And therefore, if I go back a bit, of course, you do one more test to make sure that it's neither less nor greater, so then it's equal. So you can implement binary search trivially in terms of lower bound. Now, consider the efficiency of this algorithm. This algorithm, by the way, I'm using slideware here, so I'm using BEVP, right? Begin, end, value, predicate, right? So it's just there's no space on the slide too. But this algorithm, if you notice, it has no early return. It goes up until it exhausts the entire search range. So it's always going to do worst time. worst case timing. It's always going to do log to n iterations. It's going to have the interval at each step, and it's going to do a total of log to n iterations for any n and for any search value. This other algorithm, the violet ice, is actually has a chance to return early if it's lucky enough to find the value. It's going to return earlier than log to n. So my question to you would be, which is better and why? And you just shout. Okay, so I heard like, blah, 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 blah. That's right. Correct. Exactly right. What happens here is that this guy does 2 comparisons per pass, per loop, per iteration, right? Whereas binary lower bound is going to do 1 predicate invocation per iteration. Now, it's true that sometimes if you're looking at integers and stuff, it's possible that the optimizer is going to compress these 2 into a single, into 1 comparison and then 2 conditional jumps. But essentially, STL operates at predicate level, and you know what the predicate is in general. So essentially, this algorithm does more calls to the comparison predicate. And that's the thing. However, there's still a doubt, because wait a second, this could return early. So we have an algorithm that does more comparisons per iterations, but fewer iterations. And we have another algorithm that does more iterations, but only 1 comparison per iteration. Who's the winner? Obviously, because everybody in the STD space is implementing things this way, they gotta know something we don't, right? They have some access to some secret information. So let's take a look at the expected number of comparisons. And I promise there's gonna be math, not much more than this. This is the expected number of any random variable, and it goes the following way. To compute the expected amount of comparisons you do, you multiply the comparisons done in each experiment by the probability of that experiment occurring. So you say, I'm going to search for a bunch of values, and then I'm going to see how many comparisons I've done for each, and then multiply by the probability of each happening. That's my expected number of comparisons, sort of a glorified average, right? Now, if all probabilities are equal, as in a uniform probability of searching anything, which is the case for our experiments, we're going to say all probabilities are equal, so essentially we're going to have the average of the comparisons for all cases. But that's not easy to do, right? I mean, come on, it's not a simple thing to look at. Therefore, let's ask ChatGPT. I'm here like, that's literally what I heard. Okay. So let's see how could ChatGPT help. First of all, I gotta tell you this. I broke any number of copyright laws. I put the logo of ChatGPT here for any slide where ChatGPT helped me. Okay? So that we have a measure of how much work I've done versus how much ChatGPT has done for me, right? And ChatGPT here did a lot of nice work. Essentially, it was like this. If you take ChatGPT at a high level, the first red command, given the classic binary search, give me the expected number of comparisons. It did not do well. It did not do well. It's, how's your day? No, it didn't do well. And then I asked for, I actually sat down, pen on paper, and I computed the average number of comparisons, and I came to an open formula series. And it reduced to 4 times 1 plus 7 times 2 plus 10 times 4 plus 13 times 8 plus all the way to log to n terms. So that's essentially the core of the computation. And who can do this in half a day? Okay, you can do this in half a day, right? I mean, but it's going to take you half a day, right? And it took me half a minute. Because I sat down, pen on paper, I got a series, and then I asked the green questions that worked. And notice that the green question is not very different from the second red question. It's just a slightly modified formulation of the same problem. Sum these numbers from 0 to log to n. Yeah, I know what you mean now. And this is actually an important tidbit, which we're going to revisit later, which is there is a large amount of prompt sensitivity in ChatGPT that you should be mindful of. If you get it wrong, assume there's a way to get it right. Don't laugh. Right? So, okay, so it's summing this. And it got me this not very simple formula, which is kind of difficult. I verified it for a few ends, and it worked, and I was happy on my way. Now, here's the thing. Pen on paper plus ChatGPT is a lot better than just pen on paper alone, right? Save me maybe half a day, maybe a couple of hours, maybe an hour. I'm not sure how lucky I would have gotten. Probably I would have, I don't know, do the continuous extension of the function and then do the derivative. It's kind of a complicated thing to do the series, right? And now, this is interesting because not only saved me half a day, but it motivated me to continue going. Because there are many things that, there's all this cognitive load on people, like, oh, should I embark on doing this? Oh, it's going to take me half a day. No, I better just not do it at all. But with this, you actually get motivated to, oh, I can do it in a minute. And therefore, let me do something else now, next, which is going to take me also a shorter time because of ChatGPT. So there's the opportunity cost in addition to the actual savings. The absolute classic problem of all graduate students and many people in research is not that you don't have ideas. It's that you're not sure what ideas to work on. And it's like, you wake up one morning and it's like, I could work on this, that, and the other, but I'm not sure which is going to bear fruit. And therefore, I'm blocked. I'm not doing anything at all. So I'm kind of in this state of paralysis. With an instrument like this, you can actually try things quickly and they see quickly if they work or not. So then I was like, okay, fine. So let's take a look at the simpler thing. I didn't even bother with ChatGPT because the expected time is log to n. It's always the same number of iterations. So that was easy. I didn't need to ask ChatGPT. So which one is better? So log to n or this guy? What do you think I did? ChatGPT. Of course. ChatGPT. Plot me this stuff. Plot this stuff for me, please. I didn't even bother to get the close, formal, I didn't compare these two functions and see which is, no, just plot this stuff for me up to 1 million and let me look at it. And I was happy that actually the violet ice is inferior to STD lower bound as it's implemented. It turns out that even if it has a chance to return early, the fact that it does 2 comparisons per pass is going to affect its performance negatively. And let me make a quick point here because that's an insight that I think is interesting. So let's get back to the basic algorithm here. All right, so for how many elements let's assume we search for every element in the array, 1, 2, 3, everything. For how many elements am I going to do the maximum number of steps in this case? 1, I hear. Other opinions? Half. Okay, half with a British accent. Thank you. That's correct. In both, even with my accent, it's still correct. Half. Because essentially the way it goes is you gotta collapse the range all the way. In 1 step, you can eliminate 1 element. In 2 steps, you eliminate either this guy or that guy, whichever side you want. So you can eliminate 2 elements. In 3 steps, you get to eliminate 4 elements, and it grows with powers of 2. And at the last step, in the worst case, you're gonna have essentially all the odd elements, all the elements at odd indices are gonna be eliminated in the last step. So actually, the fact that it returns early is not all that great, because in half the times, it's gonna do its worst, right? So that's kind of a hand-wavy explanation that should help us develop an intuition for why that plot is the way it is, right? By the way, the plot is copied from ChatGPT. I didn't have it generate some code that I then ran or whatever. I have the plot. It's a PNG. And by the way, I should say it's a low-resolution PNG. I assume that the folks at OpenAI did not want to pay Mathematica for high resolution. And they said, because it is Wolfram Alpha. So they said, let's cut a deal here, and the high resolution is like twice the price. Oh, no, thank you. We'll take the lower, and people can't see what's going on here. Okay, so far so good, and I'm happy. But let me ask you this. Why don't you actually use directly Wolfram Alpha or Mathematica, Jupyter, whatever, all of these programs that do symbolic math and do plotting and do all the nice things? And I'll respond with a quote. Androids have one great advantage over specialized robots. They can use tools and machines that are intended for humans. So you have all of these machines that are already built for humans, and then you get Android robots to use them all, as opposed to building a variety of special purpose robots and tools. Who said that? Who said that? Raise your hand. Thank you, Isaac Asimov. The Caves of Steel, Chapter 1. Quote found by Google Bard. Or maybe it's a good hallucination anyway, so, I'm okay. I couldn't verify, I don't have the book. I remember I read it a while back, and I remember there was a quote. I asked Google Bard for, the approximate code, and it says, oh, I know what you mean, this. So take it or leave it, right? So essentially, this is a metaphor for what I want to say. Instead of using a specialized program for math, a specialized program for plotting, a specialized program for generating code, a specialized program for whatever, I'm going to use one program that's going to allow me to do everything. And then it's like, oh, ChatGPT, do this for me. And then it's going to do this. And then I say, oh, how about that? And then I continue the conversation in natural language, and it uses on occasion math, and on occasion it uses natural language. With Wolfram Alpha, you can't do this. It's a relatively obtuse, by human language standards, it's a relatively obtuse language and way of doing things, and I don't want to learn it. I want to keep on going in natural, in natural language and mix a variety of, because I could say, here's the thing. So this plot, for example, I could say now, oh, draw me like in different colors, or draw me lines, or draw it on a different scale or whatever, and it just does that. But I tell it in natural language. I don't tell it in, I don't need to change code, right? So big difference, right? So I hope my point has been made. So, okay, so we are at, quite a few minutes in the talk here, and we're like, okay, so we looked at binary search, we looked at lower bound, we discovered that the standard library implementers know what they're doing because they did it the right way. We plotted things, and we can go home. I mean, where's the progress, right? Actually, I would say there is a problem, so let's take a look. Before we take a look at what the exact problem is, I want to talk about a mechanism, a way of doing things in binary search, which is called biasing, in a positive way. Right? I'm biasing it in a nice way, right? So this is the thing. I generalize a bit this lower bound by saying, instead of saying cut takes size byte 2, I say cut takes A times size byte B. So I generalize that ratio. And I could choose A and B any way I want, as long as the ratio comes to less than 1. Right? So then I can say, oh, wait a second. If you're exactly smack 1 by 2, it means you're unbiased. You give equal chance to things on the left and to things on the right. Okay? So far, so good. But let's say I have an intuition, I have a heuristic that the search value is somewhere on the left side. In that case, I may want to bias it to the left. And I want to say, oh, let me choose an A by B that is less than 1 by 2. And it means we're left-leaning. Okay? We're leaning left. Otherwise, maybe I choose greater than 1 by 2, and I'm right-leaning. Okay? Interesting. So if you go all the way to the left, you're on the extreme left, you're a communist. Right? If you go to the extreme right, you're a Nazi, I guess. I don't know. Right? If you're in the middle, you're kind of a social democrat, nice, middle of the road kind of person, right? I don't know if you're in negative, Taliban, I don't know what's happening there. So you want to choose this bias in a way that supports your hypothesis to accelerate the search. Things are still going to converge, but they're going to converge slowly if you chose the wrong heuristic, and faster if you choose the right heuristic. Now, there are two notable midpoints, which we're going to talk about later, so please commit them to memory. Center left and center right. Right? Moderately liberal, moderately conservative, right? Center left would be halfway between half unbiased and totally biased, and that would be 1/4. And center right would be halfway between totally unbiased and totally biased, Nazi, that would be 3/4. So when I say center left, it means this is my best guess for something. I'm leaning toward the left side of the array, but I'm not sure by how much. I'm not sure exactly what the distribution is, but I have a hunch somehow, and we're going to discuss how exactly. I'm going to have a hunch that without knowing the exact distribution, the search value is somewhere in my left side. So that would be the biased binary search. So let's see what's going on with binary search and failed searches. So let's discuss, so successful search is very nice. We find the bonds and everything. And let's discuss what happens with failed searches. And here with this thing, so the green bullets here are like found values. I find like 188, 214, etc. And we have some red squares, which are failed searches in between the values, right? So maybe I'm searching for 200. And that's going to fall in between those two first values, right? So that's my first case. I have a success case, and I have a failed search somewhere in between the existing elements. And I have a red triangle here on the left. Take a look. So I have a triangle, which means I search something that is smaller than everything. And I have another case, that the third and last case, which would be I'm searching for a value that is larger than everything. That would be the other triangle. So I have three failure scenarios. In between, all the way to the left, all the way to the right, and these are my three failure cases. And traditionally, the way research is done and the way proofs are done is you assume that all three are equally probable. You actually not even. You assume that there's only one possible. You assume that for each, you assume that exactly the red stuff on this figure, this is how you do the analysis. You assume that there's only one search in an experiment that's going to be all the way to the left, one element that's going to be all to the right, and it has an equal probability of being just like any value in between. So that's the traditional way of doing things. And it makes for a simple analysis because you have a nice decision tree, and it's kind of a nice thing, and you have n matches and n plus 1 mismatches, and the analysis is easy, and the math comes very nice. But I object. Because I've run a number of experiments, I've actually not experiments even, I run real-world code, whereby it turns out that the probability of you searching outside the bounds is quite larger. I have more triangles than red squares. And what is the optimal algorithm for that? Sorry? Check the beginning. How about the end? Check the end. Check the beginning, check the end. And then proceed with the standard. Thank you very much, Shakar. We're going to get there. When are you liable to search for out-of-bounds values? You may have grouped sort values and scattered search values, which is an absolute classic scenario. You have a number of strings, you have pre-allocated memory, you have whatever you have, and you're going to have a few values, and there's going to be a bunch of other values. And simply like intuition is like there's more outside than inside. Come on, right? You may have theoretical data versus measure. You have outliers, you have strike values, you have expiration in stock market options. They come theoretically out of bounds, and then you eliminate them, but you still search for them. List of reserved allocator assigned IP addresses in a router. You're going to have a bunch of addresses coming, and just a small list is going to be your reserved or statically allocated IPs. The search set is small. If it's small, all of a sudden I have, by definition, a lot of values outside the set, right? I'm going to have, if I look for special values in a list of integers or words, if I search for pointers in area of allocation, there's very high likelihood that the pointer is going to simply be outside what I'm looking at, right? Even in Gaussian normally distributed data, the probability of something being outside one standard deviation is 32%, and I'm still looking at even beyond two standard deviations at 5%. all of the height challenged distributions are going to have this problem, right? All of them. So if you have this fat tail distribution, it means it falls slowly, and you're going to have a bunch of searches that fall outside by nature of the distribution, the probability distribution, right? So there are many examples of this situation whereby instead of searching for many in-between values, you're actually searching for quite a few out-of-bounds values. So clearly for this extreme situation 1, which is essentially the classic textbook binary search, we have 50% successful searches, and we're going to have 50% unsuccessful, and that's how the proof goes. But my observation is that statistically, you're going to have only 2 values out of bounds, which statistically for a big N is 0%, right? Extreme situation number 2 would be what we're going to look at next, which is most of the failures are outside the bounds. So I'm not having any failed searches inside, but I'm having a bunch of them less than the smallest or greater than the biggest. So then, what is the optimal algorithm for this extreme case? If out-of-bounds searches are so frequent, as you say, can't we just test the extremes first and then use STD lower bound, right? Per the proposition that was made right here. Who has an idea about this? Is this a good thing to do? All right, so let's go back to the first slide. And remember, what's cool about binary search? What's cool about binary search is the fact that I'm not focusing on finding things as much as eliminating candidates. If you have a bunch of things that may be on the left, fails, like triangles, and you have a bunch of stuff that may fail on the right, how do you eliminate most possibilities with one comparison? Who said middle? Thank you very much. You cut in the middle, and that way you eliminate half the possibilities in all cases. Right? So you look at the middle first, and then you eliminate half, and then you look at the other extreme. So with 2 tests, you got rid of half. As opposed to looking first at the boundaries, and you do 2 tests, and you got rid of nothing. Right? Let me show you how this works. So testing both bounds actually is a waste of time. The first step, by essentially information theory, the first step should always cut the array in the middle. That's if you come with one thing from the stock, it's going to be whenever I do binary search, without even thinking that my first rule of thumb is I'm going to cut things in the middle and eliminate half of everything. That's the absolute best decision you can make. Well, there's interpolation, all that, but we're not talking here. We're talking, we don't know the statistics, so essentially cutting the middle is the absolute best decision you can ever make, right? For example, if we check the extreme first, let's say we're looking for that 650 in between 2 elements, and then my first thing is going to be, let me check against the left extreme, and then let me check against the right extreme. And I spent 2 comparisons, but I got not a lot of information because the rest of the array is still a good candidate for my matches. So that's not a good move. The right move is checking the middle first. I'm checking the middle, and then I eliminate half the elements. Boom. And I'm done with these guys. I never look at them again. And then I check the whatever bound is left. If I eliminated on the things on the left, I'm doing in mirror here. If I'm eliminating things on the left, as in this example, the next thing I'm going to do is look at the extreme right. If I eliminate the things on the right, the next thing I'm going to do is look at the extreme left. And that's how the cookie crumbles, right? I mean, it's simple. We spend 2 comparisons and we eliminate half of the candidates, right? How could ChatGPT help with this? I talked to it about this. We had a chat. It did not fare very well. It kept on going. It doesn't do things that haven't been done. It's just like, yeah, it's a good idea to check the extremes. And I say, but no, actually there's something better you can do. No, there's not. So, but anyway, credit goes to where credit is due, right? So optimal algorithm, oh, I put my face here because, right? So whenever I do the work, I'm gonna put my mugshot there. Okay, so optimal algorithm for extreme situation is like very simple. Cut in the middle, and then whatever side is left, you cut the extreme, and that's pretty much the code. I mean, it's not, it's not rocket science. I'm going to say, let me do less of the mid. I'm going to take the midpoint here, and then I'm going to say, is the midpoint less than the value? Then I'm going to go to the upper half and check the extreme there. Otherwise, I'm going to go to the lower half, and the last line of this algorithm forwards to STD lower bound, as I promised, right? It's a simple algorithm. And it works great if the assumption is correct that most failed searches are going to be way outside the array bounds. But as life has it, it's not always like that, right? But you said it costs you only one extra comparison. When you say one extra comparison, already a baby seal has died. You see what I'm saying? It's important. Okay, thank you very much. So, the code for extreme situation number 2 is easy. So now we're looking for a trade-off. We have code that works best for the textbook case. We have code that works best for this extreme case. And where's the middle? Where's the piece? So extreme one, the classic algorithm, we have no or very few out-of-bound searches, and it's best to cut half first and half of the half again next time. Extreme 2, we have very many out-of-bound searches, and in that case, we're going to cut again in half first, and you're going to look at element 0 or element n-1, depending on which side you chose, right? So these are the extreme. Where's the middle ground, folks? Shout. Louder. You go left, bias left, you go right, bias right. Thank you. The best people are in the last row. Thank you very much. Exactly. We don't have a priori knowledge about where things are. So we're going to do the best heuristics we can, which is you cut and then you go bias, center left or center right. And that's your best guess. That's the best heuristic you can demonstrably, right? So splitting the difference can sound like an engineering decision. It's actually a very simple mathematical thing. 1 by 2 divided by 2 is 1 by 4. Thank you very much, QED, right? So cut at half first and then go right or left center biased by 1 by 4 or 3 by 4. And that's the best guess you can choose, right? Awesome. That kind of bias search is going to quickly eliminate elements that are out of bounds, move toward the bound. So it's going to diverge real quick. And once the out of bounds possibility is eliminated, and I did find something that is less than, I'm going to focus on finding the exact element with the standard binary search, which is optimal for closed bounds. So it's a slightly more complicated algorithm, but nothing to be afraid of. Skewed binary search. Step 1, cut in half. Remember, the only thing you need to remember. Cut in half, eliminate half the possibilities, continue with the left side, the right side. Then a number of steps you're going to go biased by 1 by 4 from the margin, either 1 by 4 on the left, 3 by 4 on the right, introducing skew toward the bound. As soon as you found something that is eliminating the out of bounds possibility altogether, you're going to finish with classic binary search. And that is the best algorithm under the hypothesis we discussed. So let's implement this stuff. I know you're tired, but I put these red things around important parts. Now, okay, once this talk is online, you can actually sit down with the code and watch. But, I think the intuition is pretty simple, right? And it's pretty clear. So I'm going to compute the middle first, as I promised, and then I'm going to compare the middle. And the middle is less than strictly than the value. Then I'm going to be center-right algorithm biased in the upper half of the array. And as I promised, I'm going to go by 3 by 4. So I'm going to be biased to the right because I want to get quickly to the right bound. Otherwise, I'm center-left biased in the lower half, and I'm going to go divided by 4 instead of 2 as the classic algorithms. I'm going to be biased to go quickly to the left edge, right? So again, I cut in half, and then I'm going to try as quickly as possible to go to the boundary, so I eliminate all of out of bounds values. And at the very end, when I'm done with these steps, I'm going to say, complete the bounded search with STD lower bound, which is optimal because the search is now closed. There's no possibility of anything being outside. And we just proved that actually that's the best way to go about things. So that would be the skewed binary search implementation. And that was a collaboration. Look at this. Like it was, Irene and I, ChatGPT and myself. It was awesome because I told ChatGPT, do this, and it generated code with bugs, but that's okay. I fixed the bugs, right? How did it help? So first of all, it agreed it's a good idea. It did like it. Thank you, ChatGPT. Thank you, robot overlords. So it did say, oh yeah, that's interesting. I didn't think of that. Of course you didn't, because you have no training data for that stuff, right? It generated a buggy but easily fixable implementation. It suggested the name of the algorithm. This is the funniest thing. It took credit for the skewed thing. It said, oh, actually skewed binary search, that's a cool name. Yeah, thank you. All right, thanks for taking all the credit from me. And it greatly helps with tests and experiments, as we're going to see below. So essentially, there's been a number of, trials I've made, and a lot of false starts and everything. And having a possibility to quickly iterate an experiment is a game changer, because otherwise, as I said, there's like this cognitive overload in which I could try this, that, and the other, and each takes like an hour. I don't want to, I'm just going to do this, and it's the stupidest thing, right? So you want to try many things quickly, right? Parentheses, Wright brothers, the inventors of the airplane. What was the secret? They iterated very fast. So this kind of a documented thing. They made their airplanes out of balsa and paper and cardboard, and you'd be scared to see those, right? So they made their airplanes, they had an iteration time of weeks. And the rest of the nascent industry had an iteration time of 6 months. So they built 6 months of prototype, and they're like, okay, let's build another one. 6 more months. And these guys with balsa and with paper and cardboard and stuff, and I don't know, duct tape, I don't know if it existed at the time, whatever they had instead of duct tape, I don't know, saliva, whatever, right? And they quickly iterated, it boomed, oh, no problem, let's fix it, they did it. And they had this iteration time that greatly helped them. This is what ChatGPT can do for you with coding experimentation. So, okay, so now for a change of tack, how about STD equal range, which is an even more interesting algorithm. It returns both the left bound and the right bound, assuming there's more than one value within the range. So I'm searching for 50, and let's say I have an array with 1 million values, and there's 10 50s in there. I'm going to find both boundaries. I'm going to find where it starts and where it ends, and everything inside is a 50. So the typical implementation uses an interesting hybrid approach, whereby they start with the classic violet IC algorithm, and when they actually step into the 50s, the value that's found, then they're going to look for the left bound and right bound right there. So let's take a look at the implementation. It's not simple. Again, we're looking at an intuition more than oh, you have an index wrong there, right? So it's going to take, again, the iterator, the type, search, and whatever, and it's going to return a pair of iterators, the beginning and the end, right? Now, okay, so before we even get into this, you are engineers. How would you do it? You have 3 minutes to implement equal range. How would you implement it? Schedule pressure, 3 minutes, implement. What? Lower bound, upper bound. Thank you very much. Good guy in first row. Thank you. But low speaker. Speak up. So, awesome. Lower bound, upper bound, and I'm done. I'm doing more work than necessary because, I do a lot of stuff for the lower bound. I do a binary search for the lower bound. And then I go again for the upper bound. So that's kind of more work than necessary. So then let's look for a better approach, which is what's found in STL right now, which is, oh, let me start like this. I'm going to go, and they use the indexes too, so that's kind of a detail. So let me cut the array in half, and then I'm going to look in the violetized style. I'm going to look at the predicate of value m and predicate of m value, And I'm going to iterate and have the interval. But interestingly, once I found at least one element that's equal to one searching, I'm going to say, oh, I stepped in the poodle. So now let me see what's equal to the left and what's equal to the right. And I found my range. And what's nice is that once you've done a few iterations, you actually restricted your area searched by a lot. So you're liable to not do a lot of search at the end here in the lower bound and upper bound. But I still have a few critiques. By the way, as ChatGPT, it didn't do much. Right? So that looks good. So remember, we discussed the validatize algorithm. It's branchy. It does 2 tests per and 2 branches per iteration. And we just said it's actually not that fast. And it's going to work well if many equal elements present. So I don't do a lot of searching before I step into the equal range, and then I'm going to do the lower bound and upper bound. Plus, once I actually stepped into the range, the found range, lower bound and upper bound are equal opportunity. They're going to work just as well for 1 element or 0 or n elements. They're going to give equal chance of any equal range length. And let me ask you this, my friends. When was the last time you searched in an array of 1 million values or equal? Okay, when was the last time when you searched in an array of 1 million values of which 1 million minus 1 were equal? And I'll keep on going. Actually, ChatGPT did want to go 1 million steps over something. Long story. So anyway, so clearly, if I'm searching for a range of equal elements within a larger sorted array, it's very likely that the probability of me finding a long range of equal elements decreases with the length of the range. It's not the same chance that I'll find 1 million equal values in an array of 1 million and 100. This is true for virtually all data. Aside from the constant probability, the constant distributed function, all probability distributions are going to show some decay with the length of the equal elements. Uniform, Gaussian, fat-tailed, you name it, right? And real-world data is going to be like that as well. So what we want is to be proximity biased. So you want to give more chance to short ranges than to long ranges of equal elements. And that's what that's the interesting tidbit here. That's the insight. And that is, ChatGPT did not come up with that. It couldn't. It did not have that intuition. So it's good to kind of remember that there's some stuff, high level, like kind of intuition that you need to have, right? So here's the idea for equal range. Step 1, we're going to use classic lower bound. So remember, we have the array. We take the classic lower bound and we found the left edge of my searched equal range. From here on, there's going to be 1 or more equal elements. The probability of there being many equal elements decreases with the number of equal elements, right? So I'm very likely to find 1 or 2, and less likely to find a lot. So then I'm going to do another binary search, an upper bound. As he said, in a crisis, what do? Left bound and lower bound and upper bound. So when I'm not in a crisis, I'm going to do left bound, and then biased to the left upper bound, a social democrat upper bound, center left upper bound. And that way I give more chance without knowing exactly where the probability distribution falls. Without knowing exactly, I do have an intuition, a heuristics, a possibility that actually shorter ranges are more probable than longer ranges. And because of that, I'm going to bias mathematically by 1/4 my search. So let's take a look at the center left STD upper bound. So that would be a different version. It wouldn't be STD upper bound. It would be a different function, different algorithm. And it's actually 2 duplicated pieces of code. Thank you, ChatGPT. So I generate 1 loop here. And as soon as I overshoot, I'm going to break out of the first loop and I'm going to go for the classic upper bound. Now, why would that be? Because upper bound is going to aggressively move toward the left, right? That was the whole premise. But as long as I overshoot and I move inside the equal range, I'm gonna go back. How do you go back? With a standard upper bound. Because now you know that's the optimal algorithm. So as I promised, the first cut is sized by 4 and the second cut is sized by 2. And otherwise, the algorithms are pretty much, the two sides, this is a single function. But the two halves of the function are identical. I could have used a variable here. Why did I not use a variable? I know you have the answer. Why didn't I use a variable that I start with 4 and then I assign 2 to it? Shout. Sorry? Thank you. Dividing by a constant that is power of 2 is going to become a shift in the lower, right? It's going to become a shift. It's going to be a constant time. It's going to be essentially like zero time because it's going to be pipeline with a lot of other things. So it's going to be a very cheap operation. Whereas if you divide by a variable, wait a second, we have some work to do, right? Sorry? Why don't I use a variable and shift? I didn't try that. Thank you very much. That's a great idea. All right. And ChatGPT did not come with that either. It wanted a variable, and I said, no, I can't. Actually, I tried the variable. It was so slow, it was unbearable. So, okay, so this is the right way to implement a center-left upper bound. You essentially start with a constant 4, and when overshoot, you're going to continue with constant 2. So, awesome. So the proposed equal range is going to be, as I promised, lower bound and center-left upper bound. And I'm going to return the 2 iterators. And I'm done. So that's pretty much the story. We have intuitions, we have hypotheses, we live, we test things, we use these algorithms, we figure out things, and then we say, according to this hypothesis, Okay, all good? Okay, so this got, so according to our hypothesis, what is the most efficient solution mathematically? ChatGPT is going to help every step of the way in a variety of ways, right? So pretty awesome. Let me show you how this center-left upper bound is going. So let's say we have these 2 identical values, 214. I hope it's visible from the back. It's a big screen, right? Can you guys see from the back? Thank you. So I'm having these 2 identical values, 214, somewhere toward the left of the array, and I'm searching for equal range of 214. So, first we call like left bound, so we eliminate those, those elements. I'm not going to insist on that. That's the classic left bound. But for the right bound, I have the elements that are still in play here, and I want to find what's the right bound. So here I'm going to aggressively move to the left. The remaining element size by 4, which is 394. That would be the 3rd element here. Whereas the classic upper bound would go all the way to 564. So you see how I'm really quickly going to the left as opposed to the classic upper bound, which is going to take me somewhere in the middle of the array. So I really I'm narrowing down to 394, and I eliminate a bunch of values in one shot. I eliminate 2/3 of the value. If I'm lucky, in the best case, this center-left upper bound is going to do log 4 of n steps because I'm eliminating 3/4 of the elements at each iteration. So it's going to be log 4 steps, which is quite, it's double. It's quite the improvement over log 2. So awesome. I eliminated a bunch, and then I'm going to compare. I have 2 elements left. I'm going to compare with the 0th element. And then I'm going to conclude that this can be eliminated as well. And finally, I found the 362, and I'm done in 3 steps. The classic algorithm, if you go through the steps, is going to do 4 comparisons. And again, as I said, 1 comparison is pricey. Now, consider this. For 1 million element, how many comparisons, what's log 2 of 1 million? Quickly. 20, thank you. So looking at 20 comparisons. So if I save 1, I'm already like 5%, right? If I save 2, it's 10%. It's actually, you have a budget of comparisons that's very small. It's very difficult to improve binary search because you can't sit on it too much. You can't sit on it too much. Like sorting, sorting is awesome. I'm going to go through the array once, drink a coffee, Go again, see how many equal elements I have. You can collect there are algorithms that actually make one pass to collect some statistics, and then they decide what the heck to do. But with binary search, you don't have the time. You are already, by the time it's called, you are already in a time crisis. You're already out of time. It's like, oh, quick, let me divide, do this, do that. So you don't have time to collect statistics and make hypotheses and do things. So if you had, it would be really nice, but you don't, right? So you gotta really quickly make heuristics and use them. So we saved a number of comparisons, so pretty awesome. And here I'll show you a few experiments for this. And with experiments, this is where ChatGPT really shines. So that's pretty awesome. Thank you for the picture. Yes, it's an interesting thing to take a picture of. So ChatGPT helps a lot. It put together tests and benchmarks for me. It wrote code for reading files, massaging data, sorting data, outputting CSV data. And then it outputs CSV for me, and then I put it back into ChatGPT, a different dialog with Wolfram Alpha, and I'm going to generate plots from that CSV data. And all of this takes minutes. It's really quick. In fact, I gotta confess that ChatGPT has did you notice that that web interface is kind of slow? Is it slow? I don't know, maybe it's my browser. Is it slow for you? Okay, yeah, so it's not me, right? It's not just me. It's like the slowest UX in the world, right? What the heck are those JavaScript folks doing? What's wrong with them? They should use ChatGPT to make it better, right? So, the thing with ChatGPT is that it's going to allow you to iterate quickly. Put tests together, CSV plots. Code is not always good. So you gotta have a bit of judgment, take a look at the code and figure it out and that kind of stuff. But if you ask me you gotta read that file and download it from whatever and do the stuff, and so I gotta do that again and again. It's kind of a mess, right? Greatly accelerating this grunt work is a key feature of these AI helpers. There's no shame in it. The goal is the result. You shouldn't take pride that, actually, I didn't write my reading a file loop by my own. Who cares? Everybody knows how to write a loop that reads from a file, but nobody wants to write it, right? Nobody wants to write that stuff. So the deciding factor is, am I quick enough to do it myself, or am I going to wait for the slowest UX in the world, right? So that's the deciding factor. Awesome. So we have STD lower bound for the 3 extreme cases, very nice. And as you can see here is that all failed. This is the worst case for our search. And we're going to search, we have a log scale here that goes in powers of 2. And if all failed searches are in bounds, our algorithm, which is blue, is going to do a few more comparisons on average. So it's actually higher is worse, right? So lower is better. Now, however, if we look at the other extreme case, all failed searches are out of bounds, we are happy campers because it's faster, it does fewer comparisons, and it's pretty awesome. So I put them both together, and I normalized, so we're looking at relative improvement compared to the standard version. The standard version is gray, and it's always at 1.0. So again, normalized, right? 1.0 is the performance of the baseline. And then lower is going to be slow down, higher is going to be speed up, right? And look at this. Just take a look at this and think through it. The red bars are a bit below 1.0. So you're losing a bit of performance in the worst case. But the upside is you're gaining 20% speed up. So you're giving up a little in a few cases for a great upside in many cases. And this is engineering. This is what they call engineering, and it's a good result, right? And I'm happy with this stuff. So essentially, I got this number of comparisons plot, and then I measured the actual time spent, which is a bit more noisy, as it happens with timings, but it shows the same trend. So that would be the actual runtime wall clock measure. So, you have a small loss of runtime for a few cases, but you have, in most cases, you're going to look at the speed up. So on balance, you're going to look at a good speed up. So that's nice. So it's a nice result. But there's an even nicer result, which even surprised even me. And it's the equal range result. How do you test equal range without being accused of false? Because you can say, I ran equal range with 2 equal elements. And then I ran it with 3. And I got improvements. Yay! I mean, how do you count how many equal elements should be in an equal range? So what I did is I took some real-world data and a real-world task. I took a bunch of words in the English language, the most frequent 465,000 words, right? It's on the internet. I sorted them, and then I said, for each letter from A to Z, give me all the words that start with A, give me all the words that start with B, and that's an equal range test because I used this lambda, right? Use this lambda. The first letter, is it less than or not? And that's going to give me equal range for A, equal range for B, equal range for etc. up to Z. Remember it was all about the left center upper bound. How much improvement do you think we could get? 50% on an algorithm that has been considered optimal for 30 years. 50%. Thank you. More than half of this applause is for ChatGPT, okay? Just to be clear. Just to be sure So looking at a large improvement because of a variety of things we've been thinking through and experimenting with, and we got a nice result here. So there's a link to the English words and everything. So pretty awesome. So again, a change of tack. Where do we go from here? So what did I do and what did ChatGPT do? What I did was I protested. I identified a problem. I was unhappy. I lost sleep, right? I came up with ideas. I designed variations of algorithms. All fun things. All cool things to do. What did ChatGPT do? He did math, and he did code, and he did plotting, and he did experiments, and he did all the grunt work. Which would you rather do? Right? I mean, that's pretty awesome. I've done all the cool stuff, and ChatGPT has done all the uncool stuff. I got to do the fun stuff. And this is actually a very important point. I got to do what 1%er coders are supposed to do, which is think of things in high-level terms and devise things in high-level terms, and then let ChatGPT do the experimentation and the reading files and all that nonsense, right? So that's pretty cool. And that takes us to an interesting, what do we do now? Where do we go from here? What's our next step? And it is my opinion that to be a good coder, you gotta have like 3 things, and all 3 are necessary. You gotta have creativity, you gotta have good judgment, and you gotta have skill. Skill is your coding ability, right? Creativity is coming with ideas, coming with good stuff, coming with good solutions to problems. That's your creativity. And your judgment is appreciating what's good and what's not good. Judgment could also be called taste, could be called wisdom, could be called, I don't know. I think I stepped on that cable and that's the problem. Okay. So there's no interruption here, is it? Okay. So the thing is, if you don't have a skill but you have the other 2, you're going to be a newbie because you can't code but you have great ideas. And it's not a good place to be in, right? If you don't have creativity but you do have skills and you do have judgment, then you're kind of a very mediocre programmer. You're replaceable. You're going to do very mediocre things and very uninteresting things all the time. So that's also not a good place to be in. And probably the worst of all is having no judgment, because having no judgment is the cause of all problems with software in this world. Because it means you're going to have skill, which means you can code. You're going to have creativity, which means you come up with ideas, but you have no taste. I mean, how much code is out there that has no taste? None written by people in this room, none. 0 lines written by people in this room, right? But probably that's the worst, because it creates solutions that exist and may work, but they're ugly, they're bad, and they're difficult to understand and maintain and whatever, right? So probably I would say judgment is the most important thing. Now, where's the AI, where's the dark horse coming, through which door does it come? And AI levels the field in terms of skill mostly. Like it's 90% skill and 10% everything else. It's the skill part. It's going to do the coding part for you. It's going to move the fingers for you. It's going to do the coding for you. You're going to have the judgment and the creativity because it doesn't have much of either. Right? So let's see. As of today, we have the creativity, finding an aspect of binary search that researchers and practitioners were ignoring. A lot of search values are out of the bounds. So that was let's say, I'm not casting aspersions here. I'm not like a big inventor here. And I'm not going to patent this. Let's be clear, right? This is not a big insight, but it's an insight, right? It's something that ChatGPT couldn't do. And I said, oh, wait a second. What about those values that fall outside the bounds? And then I designed a number of algorithms that would satisfy that assumption, right? Judgment, distinguishing good approaches from bad. So I've done a lot more iterations than I showed you here. A lot of trials, a lot of errors, a lot of like divided by 3 and divided by 2 by 3 and divided by a variety of things I've tried. And essentially what I showed you is things that worked, right? But the fact that you have judgment is you don't try a lot of stupid solutions. You try a few stupid solutions, right? If you don't have judgment, you're going to be all the way into trying the stupid things, right? And occasionally succeeding, which is the worst of all cases, right? So, and my judgment was I want to introduce bias in search just the right way. All of that thing with 1 by 4, that's judgment. It's good judgment, right? It's a combination of intuition, math, and engineering, right? Now, skill is a bunch of math code experiments, and all of that ChatGPT did help me with. But don't think that it's only about this discussion. I have another example by my friend Emery Berger, which, we're just chatting in the hallway, and it was like memoization. We talked about memoization, right? So memoization is a great it's a good thing to know, right? So if you have creativity, you're like, in this design, I have like this system that is like a scalable, large system. Memoization for this function would be awesome. So let's do it, right? Or maybe have some variants of memoization, some crazy ideas about how to do some variants of memoization and whatnot. That's creativity. Simply understanding that this system asks for memoization. Judgment is even more important because, first of all, you should know that memoization is not a typo. Right? So that's step one. You gotta know, because, in the words of Emery, how can you be a good wine aficionado, expert, if all you drank was 1 bottle of wine? I see this has no effect on you. Like, yeah, that's not a good metaphor right there. But essentially, part of judgment is experience. Part of judgment is knowledge. I say, this guy has what they call general culture. So they know about memoization, they know about, hash tables, they know about a variety of possible solutions. And that's part of your judgment, taste, wisdom, knowledge, right? General knowledge. And that thing you need. Because, just 1 second. Yeah, actually, usually it comes, while the question was, don't you need skills? The judgment comes traditional by acquiring skills. So as you become a more skilled programmer, you develop better judgment. But I have the inkling that those times are going to change now, because the next generation of programmers, they're not going to start like that. They're going to start with ChatGPT as the default. They're going to have a window with ChatGPT at all times open. Just think of this. There's going to be a window right there. All code you want, you just got to ask for it. Right? The Netflix of code. So understanding when memoization is good or bad and that kind of stuff, that takes judgment. And it's all that part of taste and everything, right? And the skill is implementing memoization in C++ or Python or Google Apps Script. It turns out that, and maybe, I'm not sure how many people here know these, it turns out that memoization in these 3 languages is completely differently implemented. Absolutely completely different. Python has a decorator thing, which is not called memoization. It's called LRU cache, which is kind of stupid because it tells you the implementation, not the concept, which is kind of. Google Apps Script has it has a persistent cache thing that I forgot about, but I don't care because I can tell ChatGPT, do memoization for me in Google Apps Script. Yes, sir, right this way, sir. Just does it for me. So creativity, judgment, and skill are things that we all need. And ChatGPT 4 is, by the way, okay, interruption. ChatGPT 4, you gotta pay $20 a month for it, right? Consider it a professional tax. Just pay the damn money. Okay? You're well paid, just pay that money, and it's your tax. It's part of the tax. That's how I think of it. Okay? Because it's the golden standard. There's no other thing that's better. I tried them all. Nothing is. ChatGPT 4 is the golden standard. And actually, ChatGPT 3.5 is not all that bad either. But you gotta have you gotta have the best, and for that you get taxed. In terms of skill, ChatGPT 4 is good. It knows APIs, frameworks. The fact that it knows LaTeX is already I'm sold. Right? It's already, okay, where do I sign? Okay, pay you your damn $20 a month for LaTeX. Okay, it knows PyChart, JavaScript, you name it, it knows it. It produces working code from a lot of specifications. However, getting back to the memoization, it's never going to suggest memoization in a larger design by itself. You're gonna have to know it. You're gonna have to suggest it, implement memoization for me. Of course, but it's not gonna come with the initiative. Judgment, a little. It derives judgment from the large body of code that it's been trained on, but that's not a lot. And creativity is lacking right now. But I would not bet money that's not gonna change in the future, right? So right now, there's a creative aspect of combining patterns. Who's tried things like prove the theorem of Pythagoras in the style of Ernest Hemingway, right? Yeah, it's kind of a fun thing to do, and it actually does a smack job at it. It's pretty awesome, right? And that's exactly something that ChatGPT is very good at, creativity by means of combining existing patterns from different domains. But it's not very good at coming with things that are completely unheard of, which was the case with our exercise here with binary search. I'm not sure in the future how that's gonna pan out. So don't forget, your creativity, your judgment are 10x more portable than your skill. And the skill is going to become commoditized. But creativity and judgment, not. So what you can do is sharpen your judgment and sharpen your creativity, because those are going to be what's going to take you to the next level. Skill is a commodity. It's like flour, sugar, it's pepper, it's a commodity. You find it everywhere, okay? And that's going to allow you either to start from 0 to 1, I know nothing about this and I'm going to start, or it's going to allow you to transfer expertise to a new language, new domain, new whatever, new APIs. It's going to be very good at generating Qt bindings. I have no idea how Qt works. It's going to do Qt for me, no problem. And I'll have the judgment to see if it's a good or bad solution, right? And I'll have the creativity to ask for the right thing. So, to summarize, for lower bound and upper bound, don't forget, first thing you do, cut at half. Thank you. Then you cut at 1/4 from the extreme, 1/4 on the left, 3/4 on the right, and you continue like that until you bound your search, and then you finish with the normal cut. For binary search, you just call lower bound, just like the standard does. For equal range, use lower bound to get the left bound, and then use center left upper bound, which is a distinct algorithm to get the right bound, and you're going to have a good time. All of these are principal choices. Notice that there's no fudge numbers, there's no fudge factors, there's no like, oh, I chose this number, it was like 0.33 and it was pretty good. You know, there's no, it's all principal decisions, and I like that a lot. It turns out that it means there's a truth somewhere in there that is, that is self-evident, right? So that's pretty awesome. As to the summary about the rest of the discussion, ChatGPT and all, let's sharpen our superpowers, creativity and judgment, which again, as Shakar mentioned very rightly, usually we acquire them by acquiring skill at the same time. But, right now, there may be different means of acquiring these, right? By means of using ChatGPT to the skill part. Let's learn how to use AI for code. We gotta adjust our attitude. ChatGPT is not a joke. It's not, it's not a fancy fad. It's here to stay, and it's going to change the way we do programming and these conferences forever. These conferences may change the content a lot, more AI content, a lot of stuff is going to change in ways that I can't predict at this time. And for now, make sure that you learn how to do prompt engineering. There's articles, there's stuff online, there's a lot of stuff about it written by folks. Just make sure that prompt sensitivity is very high right now. So the way you ask things is going to influence very much what you get. And essentially treat this thing like an eager, smart intern on a caffeine high, 24/7, ready to help at any time. You wake up at 4 a.m., it's going to be there. You wake up at 9 a.m., it's going to be there. Anytime it's going to be there on Adderall, okay? It's going to be there all the time. And the question is, what do you make fun of it because it gets it wrong sometimes? No, you gotta use it the way in a way that is helpful to you. You amplify your productivity using your tools, and don't forget, if you get the wrong result, the natural assumption is to say it's a stupid thing. The best assumption to do is I should communicate better, right? You should be a better communicator. You should learn how to do this prompt engineering thing. Betting on AI getting better is not a wise move. So don't wait it out because it's not gonna, I don't think it's gonna work out. All right, so I'm not done yet. I have a proposal. I used to be a drummer in a previous life. I did not touch drumsticks except for the chicken things. I did not touch drumsticks for 15 years. Now we're gonna end this talk, and if you want to, you're gonna give me a round of applause, but hold it, because if the round of applause is strong, is solid enough, I swear I'm gonna jam with this band for one song. Thank you very much. Thank you. All right, so we have a few minutes for questions. I know the time is late, but I know the interest is high. Yes, please.
So, the question I have, once we had calculators, people no longer had to do calculations, and some people argue we lost something in the process, like maybe we no longer realize when we got the wrong results because we no longer have the intuition if we are in the right order of magnitude. So I was wondering if we are pushing this to the extremes, do you think we would lose something?
The question was, calculators were, but I gotta say to you that these steps have been done many times in the human history. I mean, when abacus was invented, all of those philosophers were like, oh my goodness, these kids are gonna be stupid, right? So essentially the way I see it is it's inevitable and it's gonna be here, so you may as well use it to its best. I'm not sure about the implications as to, what's gonna be bad. Mental math and all that good stuff did have its thing, but my kid is in high school and they have a required calculator which plots things for you and is colored. It has a color monitor. It could be a TV, right? So it has a lot of facilities and stuff that definitely can't be done in the mind. So I would say overall, yeah, there are minuses, but the pluses far outweigh the minuses. Thank you for asking. The other side, please.
Thanks, Andrei, for a good talk. It's
Thank
exactly
you.
what I expected. This seems like a very interesting, especially in contexts where one comparison kills a baby seal. Maybe some form of feedback-driven optimization might be able to save you, a few tenths of a percent or a few percent over where you're going, but you chose pretty round numbers because they're principled. In the reality, these are all going to be running in real-world data. It's pretty easy to collect the ratio of how many are below, how many are above, and figure out optimal numbers from there.
So the question is, let me restate the question. If you have some inkling as to what the statistics of the data is, can you do better? Yes, of course. I designed these algorithms to be replacement for the STD counterparts, which operate under no assumption at all. So they can't assume anything, right? Generally speaking, definitely, if there's room for handmade optimizations, and as I said, the task is the goal. The goal is the task. Which one was it? Essentially what you want is good results, not clean, not clean math. So I'm totally, if 0.6 works for you, 0.6 it is. I mean, it's totally fine. It turns out that the clean math numbers work best under a blend of assumptions. So that was the thing. I don't know exactly what's going on, so I'm going to choose something in the middle to get the best results in all cases. So, yeah. As to how many comparisons and stuff, like, do we save our comparisons? Do we care? I mean, how much? It turns out that these foundational algorithms may as well be very important in some applications, like median, computer median or doing searches, because people routinely consider binary search to be constant time. It's like, binary search is just gonna, unless you have cache problems, which is like very large arrays, it's gonna say, binary search is gonna take nothing. So you operate under that assumption, and if it's not nothing, then you're gonna have a bad day, right? So, yeah, good stuff. Yes, please.
Hi, can you open on slide 36?
Okay, I have a problem here.
No, it's just a question.
36?
Yeah. Is there a 3/4 over there?
Yes.
Yeah. So, did you maybe try subtracting 1/4 instead?
No, I did not try to subtract 1/4 here, right?
Yeah.
It's a good idea. Thank you. Yeah, you can save a bit on that multiplication. Yeah, thanks. Yes, please.
On the violet eyes algorithm with the 2 compares, is there any provision for calling the spaceship operator to do 1 compare?
The spaceship operator could be called for that algorithm, but it's going to lower to, no, that can help. Yeah, you're right. Thank you. So the spaceship operator is going to return an integer, right? And it's going to give you 0, 1, or -1. Yes, it's going to help. Thank you. Good point. Thanks very much. Yes, please.
Thank you very much for the talk. It was very fascinating and very inspiring.
Thank you.
And I was just thinking that you mentioned in real-world examples, the likelihood of being towards one of the end is a lot more likely. So I was wondering that you mentioned you also done more experiments, that it's really nice that we ended up with this like 1/4 or 3-to-1 skewed bias. But I wonder if within your experiments, if you did like a 7-to-1 or a 1/8 bias, what went wrong there?
What would be wrong if we cut at 1/8 instead of 1/4?
Yeah.
That's a simple variant. I actually tried that. Because I try anything that sticks, right?
Yeah.
I tried anything. It did not work well.
Okay.
That's the short answer. The longer answer is, because of the way the distributions go, trying to find the middle ground is actually the best blend of everything. So,
Great, thank you.
Yes, please.
I had an idea for the equal range thing. The first thing I would have done is, after the lower bound, is do like an exponential search kind of thing to find.
Oh, exponential search. Thank you.
And
yes.
I don't know if you've tried that or.
I did.
Okay.
Okay, exponential search. How does it go? It's also called galloping search. I literally had a slide about it, but I didn't want to take too much time. So exponential search is, you start, instead of starting from the middle, you start from the left side. And you start with a step of 1. So you look at the first element, and then you look at the second, and then if you don't find it, you look at the 4th. And if you don't find it, you look at the 8th. So you're gonna double your step with every iteration. So essentially, you're losing your patience as you go, right? And you're like, oh, the hell with it. I'm gonna do like 16 steps now and see if I care, right? And essentially, it's a good solution for short equal ranges. It's not a good solution as a replacement for STD equal range. Because STD equal range is gonna be like, we do pretty good with short ranges, we do great with long ranges. And the exponential search would be, we do awesome with short ranges, we do bad with long ranges. And my algorithm is, we're gonna do pretty good for everybody. So it's gonna be it's a good compromise. But yes, that's an excellent thing to try, exponential search. By the way, algorithms you should know, judgment, taste, wisdom, know about this kind of galloping search and exponential search and variance. Yes, please.
As part of our jobs, we often deal or work up on top of a proprietary layer. So if I ask ChatGPT how to write the responder class on top of my company messenger API, it would go, as an AI language model, I have no idea what you're talking about.
Right.
So what is your take? What are your thoughts on this?
My take is you download Code Llama, and you have a poor quality, but you have a private, essentially it can work in an air-gapped system. So Code Llama, who knows about Meta, Code Llama, right? It's not as good, but you can make it private. You can use it in an air-gapped machine. It doesn't go online. So you actually download the training, the model, you download the matrices, download the weights. And then you can use it privately. For now, that's the only solution available, but I'm sure there's gonna be a quick race to improve on that kind of stuff. For now, I suggest your company should have a policy for how do we use ChatGPT, what the limits are. As does NVIDIA. It's pretty liberal, and you can use it for a lot of code that is not secret sauce, and you just paste portions of that code. That stuff is not yet up to snuff. It's going to improve. For example, too long code and all that nonsense is still a problem. So better times are coming. Thank you. Fedor.
You kind of switched the domains on us. Your example for equal range actually had 0 out of bounds.
I'm so happy you mentioned that. Thank you. So you pulled a quick one. You're like Trump. You pulled a quick one on us. Did not work well. Which is equal range. You all of a sudden said, oh, I'm going to ignore all of those out of bounds values. And here's the thing. It's in the API. When you call std equal range, you don't expect to find 0. You expect to find many. So the assumption is in the API. There's more expectation of you finding something than finding nothing. You can use equal range with out of bounds thing. It's not going to do as well for the Google for the English words experiment because there's no out of range searches at all. Everything was in range. So it's a good point. However, I decided as a design decision, if people are calling std equal range, they expect to find not 0, but more than 0 elements. Yes, please.
Hey, great talk, thank you. So when running the left-leaning upper bound, I'm not sure, but I think maybe the right range of the upper range can be not the entire end, but like the uppermost item, like visit.
Yes. Oh,
but we need to think step by step.
So, so let me rephrase what you said to make sure I understood. The equal range algorithm calls lower bound and does a lot of back and forth, and then it calls upper bound in that clever way, right? But what I think you're suggesting is, can't we use some information collected during the lower bound step to reduce the range search by upper bound? There may be something there, I'm not sure, I didn't find it. Use your creativity. Thank you. With that, well, John should be, there he is. Thank you very much. And again, thank you so much. And after John, I'll be with the band.